and we are good to go. So what we did last time we met is we did the following. So last class, we sort of discussed how we might define the area of a region in the plane. So for example, if I just have some region like this, let's make that a little more unugly. Just some region that has a curved boundary. First off, what does it mean to define area? What does that actually mean? And if we have a definition of what it means, then the next question is, how do we calculate it? So what we did is we sort of use this intuitive idea. And when we use an intuitive idea, we notice that there's some sort of hidden, I don't want to say hidden, but there's this nice sort of pattern that evolves. And a more sophisticated way of saying that is there's this idea of a limit occurring. So what we did is the following. So what we did is we started by taking a region whose boundary is some curve y equals f of x. Now, what did we use? We used y equals x squared. So what we did, we took a region. How did we create this region? Well, we took a curve and then what we did is we restricted it to some interval. And what did we use? We used the interval 0, 1. And then what was the other boundaries? So we took a region whose boundary is some curve restricted to some interval. With the lines, what were the lines we used? We used the lines y equals 0, which is the y-axis, or excuse me, the x-axis. And the other guy we used was x equals 1, that line. So just to remind you what this shape looked like, is we did the following. So if I can sketch this again real quick. If I draw x squared, and I restrict it between 0 and 1, so what we sort of did is we looked at this shaded region. So here's what we did. Using rectangles, we conjectured the following. What we did is we approximated the quote-unquote size of the shaded region. Here was our conclusion. If we are to assign area to this region, it should be area equals a third. Now, I'm not going to go through all the details of that, but if you look at the last lecture, what we did is we took 4 rectangles and then 8, and then we just did these calculations. And what we found is that if we overestimated it with rectangles and then we underestimated it with rectangles, what we found is the number of rectangles, as they increased, those numbers approached each other. They were trapping the region. Excuse me. So the only logical explanation is if that region has size, it should be 1/3. So now we have a question though, and that question is, how do we make this precise? In general, just because we had this nice construction for a particular function in a particular region in the plane, how do we guarantee that this will work in general? And more importantly, how does it work in general? Because what we did took took quite a lot of calculation, and we were able to do it quickly last week because we have the aid of calculators and computers to help us. But you would imagine without that aid that what we did last lecture, and I would encourage you to go back and think about it, would be quite a difficult task. So that's a question I would encourage you to think about, and I would also encourage you to go back and spend some time trying to understand what we did. Before we go any further, does anybody have a question or a comment? Anybody want to say anything? I'd be happy to answer anything. All right. So, all right. Let's answer these questions then. So, the sums we used last class show up in many different applications. Now, we gave you one application. The application we gave you was area, but if we had all the time in the world, we could talk about other applications, perhaps some that you may have seen in physics or in other areas of study. We don't have time for that here, but what I need you to understand is that in general, these sums that we had, and let me remind you what sum I'm talking about. So sums of the form, so if you remember what we had something like this. We had one, say we had 1/4, and then we had like, let's think about what we had. We had 1/4 squared plus 2/4 quantity squared plus 3/4 quantity squared. And then we had, now go back in your notes, you'll see this. So sums of the form like this are called Riemann sums. Let me reword this because that's kind of misleading. So let me rewrite this. Part of my poor grammar. So I'm going to erase this and write it in better English. So I should have said that a little more clear. A sum of the form blah, blah, blah is called a Riemann sum. So this is a special case of what's called a Riemann sum. If you go back to your notes last class, you'll see that let's put it in a nice pretty color, because who doesn't love pretty colors? We'll use pink. My kids love pink. And so if I put this in a box, this is called a Riemann sum. So if you're bored, you can learn about why they're called Riemann sums. They're named after this one legend of German descent named Bernard Riemann. So if you're bored, you want to learn about them. Does anybody have a question? Hold on a second. We got some. Sorry about that. The joys of working from home. The doorbell rang. All right, so let's talk in general what these things are. And so again, this is something that's just not that easy to learn. It's going to take some effort on your part. So if I go back to the previous page, let me remind you what's happening. A sum that looks like this shows up in all types of areas. not just of pure math, but also applied math. And so we want to study them in a more general setting. So that's what we're going to do. So what is a Riemann sum? It's the following. So given a function y equals f of x on a comma b, we can construct a Riemann sum in the following way. Now remember, the intuition for this is the area. So don't forget, everything we did last class is the intuition for what we're going to write. So what you're going to do is you're going to pick n equals 1, 2, 3, so on and so forth. So pick a positive integer. It doesn't matter. It can be 1, it can be 2, it can be 3. Last class we picked it to be 4, and then I think we did 8, and then 10. We had the computer do a bunch of them. And then what we're going to do is we're going to set this number. This is called delta x, and how do we define it? We take whatever b is, we subtract a, and then we divide by n. So once we do this, next, the fancy word here is we partition AB into n subintervals of length delta x. So if you remember, if you take your time machine and you go in your brain, part of it back to last week, when we did this example, we had AB was 0, 1, and n was 4. So we broke 0, 1 into 4 pieces. What we're saying is it doesn't matter how many pieces you choose. As long as n is a positive integer, I can break it into 4 pieces, 1,000, 6, 25. It doesn't matter. So how do we do this? Well, let's actually show you what they are. So let's go to the next page, and please, if you have a question or a concern, stop me. So what are the n subintervals? Well, the first one is 0 to some point. We don't know what it is, so we'll call it x sub 1. Then the next subinterval is x sub 1, comma, x sub 2. And then we have a third, and then a fourth, and then a fifth. And then we have to go all the way up to the last one. So the last one, the last point would be B. And then we need to know what comes before that. So it turns out the way we describe it is like this. So this might take a moment. These subscripts tend to be very challenging for us to learn the very first few times we see them. So, you know, do not get too overwhelmed. You will struggle with this. So I keep writing this very sloppy. We try to make it pretty. So let me remind you, this is the first subinterval. This is the second, third, fourth, fifth. This is the nth. And we would call this, what comes before n? N minus 1. Again, these subscripts are overwhelming for us when we're beginners, but you have to bear with it. So if you want to think of this as a number line, that is also helpful too. If this is B and this is A, then you have your x sub 1, then you have your x sub 2, then you have your x sub 3, etc. And then the one who comes before B is the nth minus 1. And the one who comes before that is the nth minus 2. Now, when you're first learning this, the best way to do it is to stick to concrete examples, which we'll do in a second. It's also very useful to call B x sub n, and it's also very useful to call A x sub 0. So you look at these subscripts, and if you read left to right, 0, the first, the second, the third, all the way up to the nth minus 2, the n minus 1, and then the nth one. It's also important to note that the width of each one of these, delta x, delta x, delta x, every one of them is with delta x. Now, if you go back to your time machine to last week, remember what we're doing here. This is the same idea as last week. We wanted to draw rectangles. And so in order to draw rectangles, we needed the bases, and then we needed the heights. So the first thing we're going to do is we're going to think of each one of these subintervals as the base of a rectangle. So let's put that down there because it's very important to keep that in mind. So each subinterval is the quote-unquote base of a rectangle. Does anybody have a question? Comment? Okay, so what about the height then? How do we get the height of our rectangles? Well, so to get the heights, we use the curve. So let's remind ourselves of what we might have here. We might have, I'm going to use black here. Whoa, 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 whoa. So let's just imagine I have some particular function that looks like this. Perhaps so this is my curve, y equals f of x. And then I need points to be worried about. How about I have A, and then suppose here's B. And so what I know is I know I have, let's do a very simple case. Let's do the case where n equals 4. So this is the case down here. This is n equals 4 example. So what I want to do now to construct rectangles is I want to do the following. So in each interval, now what does each interval look like? So we have the following. They have this form. So the first coordinate is x to the k minus 1, and the next coordinate is x sub k. So again, these subscripts are very difficult for us when we first see them. But just look at this picture down here. If I'm looking at this particular interval, x sub 2 to x sub 3, who's the right-hand guy? Well, it's x sub 3. Now that subscript is 3. So the guy on the left-hand side of that interval, what number is 1 less than 3? Well, that's 2. So how do we write these intervals in general? We have to use the subscript k. So what we do is we choose any point, and it can be any. And what we do is we call it x sub k star with a star subscript. So what I'm going to do is I'm going to pick any point in here, and I'll call this guy x sub 3 star. And what I'm going to do is I'm going to evaluate the curve at that point. And I'm going to do that in all of these guys. So let me choose another color so maybe it's so clear. Then maybe this will be my x sub 2 star. And then maybe I'll use this color for my x sub 4. And then I need one more color for my x sub 1. I guess we'll use yellow. So what these are going to be is these are going to be the heights of, or at least they're going to give us a way of constructing the height. So if I come down here and choose that, then f evaluated at x sub k star gives the quote unquote heights. So if I go and get my rectangle colors, let's start with yellow. So there's my one rectangle. There's my next rectangle. There's my third rectangle, and then last but not least, I have my fourth one. So now I have 4 rectangles. Each one of them had some arbitrary height. Anybody have a question? Okay, so what happens then? Well, what happens is the following. So the area of the n rectangles is just the following. Well, what is it? It's the width times the height. So you have delta x times the height of the first one, which is x of 1 star, plus delta x times the height of the second one. And you do this all the way out to the nth one. But we typically don't like to write it this way. We typically like to write it in the following way. We know each one of them has a factor of delta x, so we could factor it out. So this thing has a name, this sum. So this is called A, not the, a Riemann sum. For F on A comma B. Does anybody have a question? Comment, concern? Okay, now we're about to do something that's going to make you guys a little uncomfortable, as if this isn't uncomfortable enough. So before we do that, I will ask one more time, does anybody have a question or a comment? Okay, so here's the thing. These sums are ugly to write. No one likes to write them down. And so what we like to do is we create a shorthand. This is not new to you. You guys have been using shorthand pretty much since you started math class. In many ways, multiplication is a shorthand for addition. In many ways, exponents are a shorthand for multiplication. So there's lots of different shorthands that we create to simplify notation. And this is not much different. So here we go. So it's convenient to adopt a shorthand notation. So what I'm going to encourage you to do, because it's not easy to get comfortable with this unless you expose yourself to it, is you need to go online and read and watch videos, because I can only do so much with this in here. The learning has got to be on you, if you want to learn this. So what we do is the following. So just consider something like 1 plus 2 plus 3 plus 4. Suppose I wanted to add that up to, say, 100. So what we can do is we can shorten this as follows. One plus 2 plus 3. We don't want to have to write this all the way out. So what we do is we create a symbol that tells us we're adding things up. So we use the capital Greek letter sigma. And we shorten it like this. So this is usually frightening for first timers. So this thing right here, this reads sum k equals 1 to 100. So that's how you want to read that. You want to read it that way. So what that means is you start with k equals to 1, then you set k equals to 2, then 3, then 4, and set k equal all the way up to 100, and then you add them together. Before we talk more about this, let's spit out a couple more examples of this. Similarly, we might write like 1 squared plus 2 squared plus 3 squared plus, say we went up to, I don't know, 17 squared. We might write this as sum k goes from 1 to 17 of k squared. So this is a shorthand notation. What else can we do? Well, we don't have to just do numbers. We can have arbitrary expressions like we had above. Suppose we had f of x sub 1 plus f of x sub 2 plus all the way up to f evaluated at x sub 27. We could write this as the sum k goes from 1 to 27 of f evaluated at x sub k. And to beat the dead horse one final time, suppose we had one half plus 1/4 plus 1/8 plus 1/16 plus, suppose we went all the way up to 1 over 2 to the power n. Now this one's a little more complicated, but if you spend some time on it, you'll pick it up. This is 1 over 2 to the power k. So this stuff has a name. This is called summation or sigma notation. So you may have seen this before, maybe in a probability. You know, these sums pop up in prob and stats and different classes. So this is the Greek letter sigma. Whew. Does anybody have a question? Comments? Okay, so we can put these puzzle pieces into a recasted definition. So here we go. So a sum of the form f evaluated at x sub 1 star plus f evaluated at x sub 2 star all the way out to f evaluated at x sub n star. If you take this sum and you multiply it by delta x, which in shorthand can be written like this. So if you take this guy is called a Riemann sum of f on a comma b. So this is a very, very important concept. Again, you know, I always repeat myself. You guys get that. But these types of sums are ubiquitous. They're everywhere. Okay, so the question is then, oh, you keep telling us they're everywhere. Well, okay, so all we've seen is that they're somehow connected to this concept of area. And don't forget, we haven't really defined area yet. We're trying to get some intuition for what it might be, but we don't really have a sort of, how do we say, rigorous or precise definition of area. And we're not going to get that for a little while. So, you have to keep that in mind. What we're, if we sort of reset what was happening, our initial problem that we stated on the very first day of class was, how do we assign area to regions in the plane? And then we spent the whole semester thus far talking about derivatives and all this stuff. And now we finally talking about area again. And what we did is we used our intuition, albeit forced intuition, because I said, hey, let's think of it like this. But under your forced intuition, what we kind of get is we get that area of curved regions in the plane has to somehow be related to this idea of taking rectangles and computing their area, then taking more rectangles and computing their area, then take even more rectangles and computing their area. Because what we saw at the end of last class, if we kept doing these rectangles and kept choosing more and more rectangles, a couple things were happening. First off, the widths of the rectangles are shrinking. If instead of using 4 rectangles, I use 8 or 800, the widths must shrink. And then what we noticed is there was this pattern of these rectangles and these rectangles were sort of coming together at the same number. And that was not an accident. That's happening for a reason. And that's kind of what we want to find out. What is that reason? Does anybody have a question? Okay, so what we want to talk about right now are 3 important specific Riemann sums. And what we did is we used 2 of them actually last week. So let's talk about that. So the first one we're going to give you is what's called the left Riemann sum. So how do we define the left Riemann sum? So we're going to do an example of this. So we need to define our xk star. What gives us a left Riemann sum? We use this formula. And this formula is best learned through experience. So we're going to do that in a second. So these formulas, again, at the outset are scary, but they're not going to be that scary in a second. And once you do an example, you'll see exactly where these things come from. Now, don't forget what x sub k is. So in general, what is x sub k? X sub k is just a plus k delta x. So this is going to be sort of overwhelming and confusing. And as I said about 30 seconds or a minute ago, don't memorize these things. You don't want to memorize them. What you want to do is use them. So let's look at this real quickly with an example before we even freak out on these subscripts, because it's really not that bad. So the standard example you need to have in your head at all times is this. This will make your life easier going forward, not just this semester, but Calc 2. So let's go to f of x equals x squared on 0, 1. So this is what we did last class. So let's recall delta x. Well, let's use n equals 4. So delta x is 1 minus 0 over 4, which is, of course, 1/4. So the best way I can convince you to do this is to always draw a number line first. Don't try to use those formulas I just wrote down. What I want you to do is I want you to draw a number line. And I don't care what your A and B is, just draw a number line. Now label your number line with the points you have. So what are my points? I have 0, and I'm going out to 1. And now I need 4 equal subintervals. So just draw it, cut it in half. What's this point? It's 1/2, but I'm going to call it 2/4. What's this point? 3/4. And what's this point? 1/4. So before I go to those scary formulas, I do this. Okay, so what are my x subscripts now? Well, my x sub 0 is 0. My x sub 1 is 1/4. My x sub 2 is 2/4. My x sub 3 is 3/4. And my x sub 4 is 4/4, or 1. Look at the pattern here. Lots of patterns hiding out here. Okay, now, this gives us the information to do a left and a right sum. So we could do that if we wanted. We're going to do that on the next page. But before we do that, let's also compute the midpoints. What are the midpoints of each one of these? Well, the midpoints are, what's halfway between here? Well, you add them up and divide by 2. So that is 1/8. What's the midpoint here? You add them up and divide it by 2. So you get 3/8. What's the midpoint here? You add them up, you get 5/4, divide by 2, you get 5/8. And then the next one will be 7/8. Those are my midpoints of each interval. So now we could write out the left, the right, and the midpoint Riemann sums. So let's do that. Before I go to the next page, does anybody want to say anything? Comment, concern? This is fun. All right, so let's go to the next page. So we can write these out. And I'm not real concerned with finding out what they are, although we did this last week. So what's the left sum? The left sum is delta x times f evaluated at x sub 0 plus f evaluated at x sub 1 plus f evaluated at x sub 2 plus f evaluated at x sub 3. That's the left sum. We could tell you what this is. This is 1/4. And then this is f evaluated at 0 plus f evaluated at 1/4 plus f evaluated at 2/4 plus f evaluated at 3/4. And then that's f evaluated at 0, which is just 0 squared plus 1/4 squared plus 2/4 squared plus 3/4 squared. And just like I told you last class, I'm not going to go to a calculator because there's a pattern hiding here. Factor out these guys and I get 1/4 cubed times 0 squared plus 1 squared plus 2 squared plus 3 squared. Now we did this last class. And then of course, if I want at this point, I'll just go to a calculator and get a number, mostly because I can. So what you end up getting is you get 14/64, which is 0.21875. So if you checked your notes from last class, you would see that we got that. For the lower, remember we did these lower these lower rectangles. That's what we had. Does anybody have a question? All right, so if we do the right sum now, the right sum looks like this. It's delta x times, now you start here. And so you plug these in, you have 1/4. And I'm going to skip a step here. This becomes 1 squared, excuse me, 1/4 squared. And this is 2/4 squared. And this is 3/4 quantity squared. And then this is 4/4 quantity squared. But that's just 1. But if I write it like this, once again, I can take advantage of this pattern. I can pull out the 4 squared and I get 4 cubed, and then it's 1 squared plus 2 squared plus 3 squared plus 4 squared. And what happens if I add this up and divide? I get 0.48, or excuse me, 0.46. .875. And then lastly, the last thing we can do is we can do a midpoint one. That's what we're asked to do. So if we turn the page to that one, the midpoint, once again, it's delta x, and then it's f. So what's the midpoint? Well, I'll just call it m sub 1, because I don't know, you know, I'll use m for midpoint. M sub 2. The third midpoint I'll call m sub 3, and then the last midpoint I'll call m sub 4. And then this is 1/4. So what's the first midpoint? Well, if you go back a couple pages, the first midpoint is 1/8, and then it's 3/8. There's a nice pattern there. So it's 1/8 squared plus 3/8 squared. Hi, Ricky. Go play, sweetie. You want your shoes on? Okay, well, Daddy's busy. I can't. Aim, can you come get her, please? Lydia, come get your sister. The joys. And then lastly, we take the fourth midpoint, which is 7/8 squared. And if you factor this out, that's 8 squared. And then what you're left with is 1 squared plus 3 squared plus 5 squared plus 7 squared. Ricky, you behaving, Ricky? Okay, so if you do the arithmetic here, which I will spare you the joys of it. If you multiply these and add them up, you end up getting 0.328125. Okay, so are you going to do this as quickly as I did? Absolutely not. But you should practice it and strive to do it, at least at a reasonable efficiency. Of course, you know, no one expects you to do this by hand for like 40 rectangles, nor would I ask you to. But you should get a feel for being able to do it with like 4 or 6 rectangles. It's not difficult to do this. And we're going to show you a couple shortcuts on the homework. Does anybody have a question about this? Comments, concerns? So what we're going to ask you to do is do the following on the homework. So you should draw y equals x squared on 0, 1, and all 3 cases: left, right, and middle. So we did the left and right for you last class, but you should do it again for practice. And you should draw the curve, and then you should draw the rectangles, and you should do this computation. This is the best way for you to learn it. And then hopefully you'll start to think ahead. You'll say, okay, what was his point of last week's lecture where we did all those computations? If you do it for n equals 10, n equals 100, n equals 1,000, 5,000, 10,000, what do you see happening? So ask yourself, so what happens to each case if n equals 10, 100, 1,000, etc.? So ponder that and get a feel for what's happening here. Does anybody have a question? Comment, concern? All right. If you do not have any questions, I say we'll end, and then we will see each other Thursday, hopefully. Well, I don't see any of you, but you guys might see me. If you have any issues with lectures, whiteboards, whatever, show, but I'll try to get that up right now. If you guys have any issues, please email me. I'd be happy to meet virtually or through email or whatever you want to do. So I'm going to stop recording.